Hi everyone. Hi everyone. So my computer's saying I have bad network connectivity again. So if the video gets wonky at any point, I am very, very sorry. I apologize ahead of time for that. I don't really know why it's doing that. I'm on like the larger frequency Wi-Fi, so I shouldn't be having this issue, but I am. So we're gonna deal with it. So let's go ahead and jump into some circular motion practice problems. So these documents are in Canvas, just like always on today's date, under this event in Canvas. Okay, so we have a block that looks to be rotating in what's called a conical pendulum. So it's rotating in a circle, and if you were to kind of think about the shape that it would sweep out, you'd see this like nice cone type shape. Okay, so I'm guessing we're going to be dealing with some circular motion. We're going to be dealing with some tensions at angles because the string is at an angle. We got some gravity. So I need to be thinking in terms of like circular motion for this type of problem. So in the apparatus shown, one end of a string of length L is attached to a block of mass M. Excuse me. The other end is connected to an axle of a motor that rotates, causing the block to move in a circle of radius r at a constant speed vt, such that the string makes an angle of theta with vertical. Okay, so I'm dealing with this angle up here. Ooh, whoops. Where'd it go? Okay, here we go. So I'm dealing with this angle up here, which is the angle with vertical, which means that the x component is now the opposite side, so that's sine, and this y component is going to be cosine. Okay. A student wants to use the apparatus to make measurements and create a graph, sorry about it, that can be used to estimate the acceleration due to gravity. The student can adjust the motor to achieve different speeds of the block. Okay. So let's go ahead and look at question 1. So the dot below represents the object as it travels in a horizontal circle at a constant tangential speed. On the dot, draw and label forces, not components, exerted on the object. Each force must be represented by a distinct arrow, starting on and pointing away. So this not components is important for us in this problem because we are going to end up having components of tension, but we don't want to include them on this free body diagram. And the way that this printed my dot is over here naturally. So I definitely have, and again, we're doing it for the block, a downward force of gravity. So I'm going to label that Fg. And then I have a tension force kind of off at an angle, but I'm actually going to label it Ft, okay, for force of tension. All right. Now, on a separate free body diagram, I'm going to draw those components of tension just in case I need them. So I'm going to have an Fty and an Ftx. And remember, because I'm dealing with this angle from vertical here, this x is the opposite side. So this is really Ft sine theta, and Fty is Ft cosine theta. Okay, so I need to derive an expression for the block's centripetal acceleration in terms of m, theta, and physical constants as appropriate, aka g. Okay, so the centripetal acceleration comes from the force that creates the centripetal force, so the force that pulls the object into the center, and the force that is pulling the object into the center is this Ftx. So that is our centripetal force. So remember, centripetal force is mass times centripetal acceleration. Okay, so Ftx is our centripetal force. Oops, there should be an x there. So Ft sine theta is mac. Now you might be thinking, oh, sweet, I can just divide by mass and I'm all set to go. But the thing is tension, Ft, is not an allowable variable. So we need to figure out another way to represent Ft. So we need another equation. So what we're going to do is use this y direction, or the y direction forces. Okay. Now in this y direction, this mass is not bobbing up and down, it's not accelerating downwards or accelerating upwards, which means that our net force in the y direction is 0. And that's really helpful to us because that means that Fty and Fg have to equal each other. So this will allow us to write out an equation for the force of tension with given variables. So Ft is mg over cosine theta. So now what I'm going to do is I'm going to take this equation for Ft with proper variables and substitute it in here. So I have mg over cosine theta times sine theta equals MAC. There's a mass on both sides, so that's going to cancel. And one thing to remember is that sine divided by cosine is tangent. So maybe that's a good thing to write down on like an equation sheet, just so you remember it. So this becomes G tan theta equals AC. We only have those variables. We actually don't even need the mass. Just because it's given to us doesn't mean we have to use it. So our acceleration is just simply G tan theta. Let me check for questions. Oops. And it doesn't look like we have any questions. For some reason, my computer is not letting me look at, oh, there it is. Okay, Q&A. No questions, we're good. Okay. All right, so then we want to use the experimental apparatus and the available equipment to design an experimental procedure that the student can use to determine the acceleration due to gravity at the surface of the Earth. Okay. So I'm going to get that acceleration due to gravity here, G, by looking at tan theta, maybe, and the centripetal acceleration. Okay. The thing to remember about centripetal acceleration, though, is that I could rewrite that as v squared over r. The reason why that's helpful is because it's easy enough for me to measure the speed of something moving in a circle, and I can definitely measure the r. Okay. So again, I'm using this equation that I just created to help me find g, because really, g tan theta is going to equal v squared over r. Okay, so I need a way to measure theta, v, and r. So I'm going to measure the velocity with the symbol v, and that's going to be measured with a photogate or something like that. Or what we could also do, instead of measuring the velocity, we could measure the period, okay, which is registered starting capital T with a stopwatch. I almost wrote time watch. Wow, stopwatch. Okay, because if you remember, the velocity of something moving in a circle is 2 pi r over the period. So we're kind of indirectly measuring a lot of stuff in this problem. Okay, so I definitely need the radius as well, which is going to be measured with a meter stick. Okay, and then I need a way to measure theta. Okay, I need a way to get the angle. So if I go back to this here, okay, I can use these distances L and R to help me find the angle. Okay, so it's kind of basic trig, right? So the sine of the angle is going to be R over L. So if I have R, which I'm already measuring, and L, the length of the string, I can find the angle using sine, which then I can plug into that tangent function. So I'm also going to measure the length of the string with a meter stick. And this experimental design type question is not going to be on the AP exam. Okay. All right. So moving forward with this experimental part, We need to describe an experimental procedure to give the estimate of the acceleration due to gravity at the surface of the Earth. Give enough detail so the student could replicate the experiment, include a diagram, assume equipment usually found. Okay, so let's say 1, we're going to measure the length of the string. That's easy enough to do. Okay. We're going to turn on device and measure the radius of rotation. We're going to measure the time to complete 10 periods, because remember, it's tough to just get one, and the period is going to be the time over 10. Okay. 4, repeat at various speeds, because it said that the motor that's running this device was variable. Okay, and of course we would want to repeat it at variable speeds because that's going to help us create a graph or something like that. So as a reminder, we're working off this equation. G tan theta is v squared over r, but we're indirectly measuring the velocity by doing 2 pi r over the period. Okay, now when you have to describe an experimental procedure, that doesn't include any analysis. So that doesn't include calculating the velocity or anything like that. Okay, so the student wants to collect the data from the experiment to create a line graph that can be used to estimate the acceleration. So state what quantity should be plotted on the horizontal axis and what should be plotted on the vertical axis to produce a linear graph. Okay. All right, so let's actually plug in this equation into V to see if we actually need to calculate the speed. So let's see. We have G tan theta is is 2 pi r over t squared over r. So G tan theta is 4 pi squared r squared over t squared r. Okay, so the t squared ends up coming down here into the denominator. So one of the r's cancel. So G tan theta equals 4 pi squared over, or 4 pi squared r over t squared. Okay. All right. So we want G. So I'm going to solve this equation for G. 4 pi squared r over t squared tan theta. And as a reminder, okay, you're going to find theta because the sine of theta is going to be that radius over the length like we talked about earlier. Okay. So I can use this equation here to help me figure out what to graph, because anytime I see a division like this, it's a slope, okay? Which means whatever is on the top is what should go on the y-axis, and whatever is on the bottom is what should go on the x-axis. So horizontally, I should probably graph t squared tan theta, and on the vertical axis, I'm going to graph 4 pi squared r. Okay. So indicate which feature of the graph could be used to determine G. The slope can be used to determine G because G is 4 pi squared r over t squared tan theta. Okay. All right, let me check for questions. That was kind of a little bit of a complicated experimental design. Would you still get credit? So it depends. So the question was, would you still get credit for writing velocity instead of period? So it depends on how you talk about getting the velocity. Like you would need to figure out a way to use experimental equipment like a photo gate timer or a motion detector to measure the velocity, and then you would have to talk about that in your experiment. Using the period is the easier of the ways because you're using a lot simpler equipment, but it certainly could be done with the velocity. All right. And that actually brings us to the end of that question. So now on to the next question, which is a gravity question. Okay, so we have 3 different planet-star systems, which are far apart from one another, shown. Okay, the masses of the planets are much less than the masses of the star. Wonderful. So in system A, planet A has a mass of mass planet, star A has a mass ms and a circular orbit of radius r. Okay, so those are kind of our initial masses and radii. Then in system B, we have a planet of mass 4 mp, orbiting a star of mass ms. So we have quadrupled one mass here in system B from system A. And then in system C, we have a mass of the planet with a star of 4 ms at a radius r. So we've again quadrupled one of the masses from the original. So gravitational force exerted on planet A by star A has a magnitude of F0. So all of these combined give us F0. Remember, gravitational force when we're talking about planets is G m1 m2 over r squared. So that F0 represents G, mass planet, mass star, over r squared. Okay. So we need to determine the magnitudes of the gravitational force in system B and in system C. All right. So the magnitude of the gravitational force on planet B by star B. Well, that's going to help us, or that we're going to figure that out by looking at the differences in masses and radius. Like I said, we quadrupled one of the masses from that initial system. Now, force of gravity is directly proportional to mass. So that means whatever we multiply the mass by also happens to the force of gravity. So we're going to see a force of gravity 4 times as large. So we're going to get a 4 F0, because remember that F0 represents the initial gravitational force for star B. The same thing actually is true for star C, because again, we're quadrupling one of the masses. It doesn't matter which of the masses we're quadrupling, they both have a direct relationship. Now, if we were to quadruple both masses, like let's say this was 4 mp and 4 ms, then we would get a 16 F0. So we would combine those quadruplings. But here, we're just quadrupling one of the masses, and therefore our answer just needs to be 4 F0. And the answer is actually that simple for that part. Okay. So how do the tangential speeds of planet B and C compare to that of planet A? In a clear, coherent paragraph length response that may also contain equations or drawings, provide claims about why the spin is either greater than, less than, or the same, and why C is either greater than, less than, or the same. So we have to answer these 2 questions and explain why. Okay, so let's first figure out how we might get to the tangential speed. Okay? Now, if you remember from gravity, whenever we have something orbiting in a perfect circle like this, it's going to orbit in a circle, a perfect circle at a constant speed. And that constant speed we're talking about is the tangential speed, meaning the velocity or speed directed tangent to the circle. So for whatever reason, gravity was to stop existing in system C, this mass planet would continue off in a straight line. That's what that tangential speed represents. Okay. So for both of these systems, gravity is causing the centripetal force, which means we can set it equal to mv squared over r, where this v is the tangential speed that we're talking about. Okay. So in both cases, we're looking at a force of gravity that is 4 times the initial force. Okay. So mv squared over, sorry, my eye is itching, r. Okay. Well, what does that F0 represent? It represents G, mass planet, mass star, over r squared. Okay. And in both instances, that 4 can be pulled out front. Okay. Now, the mass in this equation here is the mass of the planet, the thing doing the rotating. Okay. So now let's start simplifying. So mass planet goes away, r goes away. So I get 4g mass star over r is v squared. So v is the square root of 4g ms over r. So what this tells me actually is that because I can pull a 2 out from the 4, is that the velocity of B and C is 2 times larger than the velocity of A. Okay, that's what this 2 out front represents, because this would be the speed of A. Okay, so both have a speed greater than planet A. So let's first answer the question. Remember, A, answer the question. B is basic physics, C is context, or context, and D is draw it all together. So A, answer the question. The tangential speed of both B and C will be larger than planet A. Okay. This is because both B and C experience a gravitational force four times larger than A. So that's a little bit of the context. So now I'm going to start to talk about the physics. Okay. So the physics is that this force of gravity is what causes the planets to move in a circle, aka is the centripetal force. This means Fg is equal to mv squared over r. Okay, and on the AP exam for this year, you could write that out as Fg is mv squared over r, if you wanted to. In this equation, the mass of the planet oh shoot, I just realized I think I'm answering this whole thing wrong. Oh no, guys, I've done it again. Okay, so this equation that I derived, lucky me, really only works for system C, where this massive planet is still MP. So the tangential speed of only C is larger because C experiences a gravitational force 4 times larger than A. Okay. I'm actually going to erase all of this. We're going to restart this question. I'm the worst. I'm so sorry. Ignore. Okay, I'm not going to erase it because it's going to take forever. Oh, goodness, guys. Okay, so let me get some clear paper. There's a clear sheet. I'm so sorry. I'm the worst. Okay, I'm so sorry. Okay. So, we're going to go through this again. So, I'm going to derive 3 equations. The speeds for all A, B, and C. They all stem from the same idea that the force of gravity is the centripetal force. Okay? So the force of gravity for A is G, mass of the star, mass of the planet, over R squared. This is the mass of the planet. The R cancels. The mass of the planet cancels. Okay. So G ms over R, square root of that ends up being V. So here's where I messed up. In B, the mass of the planet is 4 times the mass of the initial planet. And in C, the mass of the star is 4 times the initial mass of the star. Okay. So in B, Fg is Fc mv squared over R, as before. Okay. Fg is going to be G, mass of star, 4 mass of planet over R squared. And this mass over here also needs to be a 4 MP. So I made a mistake that actually I've seen a lot of you make on tests. I forgot to carry this 4 to both sides of my equation. Why is that important, you ask? Well, because when that's the case, watch what happens. The 4 cancels on both sides because it's present on both sides. This R cancels, and the equation for the speed ends up being exactly the same. Because the only thing that's going to determine the speed in these planetary systems is the mass of the planet itself, not the mass of the satellite, because the mass of the satellite cancels. So it doesn't matter in System B that the mass of the planet orbiting the star has a different mass. The mass of the star is the same. Whereas in Planet C, or in System C, right, the mass of the star is different. So this becomes G 4ms mp over R squared. It's mpv squared over R. R cancels, mass planet cancels. The 4 is still there. So this is 4G ms over R is V squared. So V is the square root of 4G ms over R, or like I said earlier, 2 times the velocity of B and A. Okay. So sorry that I just completely messed that up. I made a simple error that a lot of you would make as well. Okay. So now I have to write out my paragraph length response. So I would write out something like planet B has the same tangential speed as A, even though planet B has more mass. The mass of the planet cancels in the equation for tangential speed, right, using gravity as the centripetal force. It's a good idea to kind of throw that in. So even though planet B has more mass, the mass of the planet cancels, and the equation for tangential speed, leaving only the mass of the star. and radius to affect the speed. Since these are the same for A and B. Whoops, too far. The tangential speed must be the same. Now, you would hope or think maybe that you were done, but remember we have to explain planet B and planet C. So planet C, however, is orbiting a star of larger mass than A and will therefore orbit at a larger speed. This is because the orbital or tangential, as they're calling it, velocity is directly dependent on the square root of the mass of the star. Okay. Whew. All right, so let me just check this again. So I got to make sure I answer the questions. I talked about the physics. I've given the context and I've drawn it all together. So planet A has the same tangential speed as A. So there's one answer that I have. And then my other answer down here, planet C is orbiting a star of larger mass and is moving at a larger speed. So I've explained how both are moving. Okay. Then if you remember, the question says I need to explain why those speeds are the way they are. Okay. So for B, I said that even though planet B has more mass, the mass of the planet cancels in the equation for tangential speed using gravity as the centripetal force, leaving only the mass of the star and the radius to affect the speed. These are the same for both A and B, so the tangential speed must be the same. Planet C, however, is orbiting a star of larger mass than A and will therefore orbit at a larger speed. This is because the orbital or tangential velocity is directly dependent on the square root of the mass of the star. So even though I didn't need to derive the equations for this, it definitely helped lead me to the right answer. Okay, so I have the scoring guide pulled up on my phone, so I'm just going to go through it and make sure I included everything. So I have 1 point earned for equating the centripetal force to the gravitational force. So I talk about that. Boop, 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 boop. I'm going to get the highlighter so I can highlight that part. I talk about that here. So that has 1 point. Okay. So 1 point is earned for a correct reasoning or derivation relating the planet's speed to the star's mass. All right, so I talk about that down here. The orbital velocity is directly dependent on the square root of the mass of the star. So I get 1 point for earning that planet B has the same speed, so I get another point here. I get 1 point for planet C is greater, so I get that point here. Larger speed. And then 1 point for writing a paragraph that makes sense. So in the example response for this, they actually have a derivation drawn out. Now you can include in questions like this, your paragraph responses, you can include derivations to help support your reasoning. On this year's exam, it is highly unlikely that you would need to do that, but that being said, you might want to on like a scratch piece of paper. I'm a part of a Facebook group for the AP physics teachers, and one of the people who has written the exam or written parts of the exam has said again and again that typing will be super easy. you shouldn't feel the need to write out your responses, that typing them will be fine. That being said, if you're more comfortable writing your response, that is totally okay. Okay, so I'm so sorry that I totally messed that up. No one's surprised, I do that all the time. I should probably look at the answer keys before I jump into this, but this way you guys are seeing me go through them the first time, which I like. So in like another half an hour, I'm going to do open office hours. Feel free to come back. Hope to see you guys there. Have a wonderful rest of the day. The sun is shining, I think, for the most part. So I will see you guys soon. Bye. Trying to hit end and it's working. There we go.